We are into bending stresses, and we learned a few intricate details about bending stresses in the last class. Today we are going to quantify them, and we are going to see how these things work. So these are all done. Let's get back to the yes. So sign convention. This is one of the important things that we have to deal with when we deal with stresses in beams, and we have to be very careful with sign convention. A slight change in sign convention will lead to different results, and therefore you need to be careful, and you have to mention your sign conventions when you do a problem, what sign convention you are considering. So as I said, the positive sign conventions are going to be something like this. Right side shear is positive, right side shear upward is positive, left side shear downward is positive, and the moment that is sagging moment is a positive moment. Sagging moment in the sense compression in the top and tensile in the bottom is called sagging moment, so that's positive. Whereas hogging moment, where compression is in the top and tensile in the tensile in the top and compression in the bottom, is the negative. Okay, so that's how we consider our shear, shear and bending moment as positive for stresses. Now, one thing to note is there are a few assumptions I wrote in the last class. There are a few more assumptions that we're going to discuss today. One of the assumptions, please note the assumptions here. One of them is plane section. So there is one assumption that is always there. Okay, material is homogeneous and isotropic. Okay, that's always there. Having said that, there are a few more assumptions. One of them is plane sections remain plane before and after bending. Okay, we will see what is that. Longitudinal axis, the length of longitudinal axis doesn't change before and after bending. So this is actually not longitudinal axis. It is neutral axis, which happens to be longitudinal axis in many cases. But okay, plane sections remain perpendicular to the longitudinal axis. This is also not longitudinal axis. This is also neutral axis. In-plane distribution of the section is negligible. Distortion of the section is negligible. Pure bending is considered. Okay, pure bending we have seen in the last class itself. I will show you what are these assumptions mean in the next following slide. So how do we, what is the objective? The objective is to go from external load to deflection, right? To relate external load and the deflection together in beams. So while doing that, we have to go through a lot of small towns. These small towns are shear force that you have to learn, bending moment you have to learn, and slope curvature you have to learn, right? So shear force, bending moment you have already learned, and then we have to learn how to calculate slopes and curvatures and what are these things. And as you see, the relationship is very straightforward. If you have a load, you take derivative of that load with a spatial coordinate, you get shear force. Then you take another derivative, you get bending moment. Then you take another derivative and multiply with EI, you get slope or curvature. Take another derivative of slope and curvature, you get deflection. Did I say it correctly? No, I said it wrongly. It is actually ulta. From deflection, if you took derivative, you get slope. From slope, if you take derivative, you get bending moment. From bending moment, if you take derivative, you get shear forces, right? And from shear forces, if you take derivative, you get external loading. And integration you have to do when you go from external load to deflection. All right, so this is quite the opposite. So I don't know, can I rub them? Yeah, well, very well I can rub them. All right, so this is going to be from deflection to slope. Okay, right. So one of the relationship you might have already done in your first year, that is relationship between moment and the external load, right? This is given by this formulation d squared m by dx square is equal to minus q, right? So qx is a distributed load given on the surface of the system, right, downward, and then d square m is the bending moment anywhere in the section. How it comes? How do you find that? It's very simple. You take a beam. Okay, let's take a beam. Take any one of the small section, dx distance. Let that be this one. Okay. So this is your section with the dx length, right? And there is this UDL acting on the surface, any kind of distributed load acting on the surface, which is given by Q per unit length. The shear forces for my positive directions will be V here, V plus dV here, and M here, M plus dm here. Okay. Now, why V plus dV, M plus dm? Because there is an external load acting. Since there is an external load acting, V will not remain constant, neither M will remain constant, right? They both will change because there is a load acting on the surface. Therefore, one of them is M, the other will be M plus dm. So the change is dm. And this is my positive x-axis, okay? Therefore, that's my positive x-axis. All right, so if you do summation of vertical forces, you get this side is V. So for summation of vertical forces, my V is upward positive. So I write V as a positive. Minus Q dx is the load that is acting from external side. Minus V plus dV. And that should be equal to 0. And that gives you a very simple relation, dV by dx equal to minus Q. Okay, this V cancels. And you get dV by dx equal to minus Q. Now, if you take moment about any of the cross section, any of the side, or from the center, whatever you want, you can do. You take moment about this line, right? Or you take moment about the central point, or you take moment about this point. What will you do? You will get dm by dx equal to v. Okay. Once you get dm by dx, so this is force balance. And this one is moment balance. Okay. When you combine these two, so dm by dx is v and dv by dx is minus q. So if I put this back here, what I get is d square m by dx square is minus qx. Okay. Now remember, this minus sign here is coming because of the sign conventions I'm considering here. Some books will follow a different sign convention, and then you will not get that minus sign here. Okay, it's a second order differential equation if you note. So what we have assumed here, upward V is positive and anti-clockwise moment is positive. That's what we have considered. So these are my positive sign convention. Positive. Okay. Right. If somebody assumes, some books assume that Q downward is positive, many books do that. Q downward is positive, then in that case, this will be plus Q of X, not minus Q of X. So that also I've written here so that you don't get confused with sign convention from other books. Many of the books that are related, that are a little bit old in mechanics, slender material, they will follow that sign convention that Q of X downward, the load downward is positive. Load is always downward positive. Okay, so if you look at this equation now, this is a second order differential equation. Okay, and this is M is bending moment. Okay, it's not moment acting on the surface, it's a bending moment. And Q of X is a distributed load at the top of the beam, transverse distributed load. It's a second order equation, and therefore it will need two boundary conditions to solve. Right, it will need two force boundary conditions to solve. Now, force boundary conditions in the sense either moment or force, right? Either of them will be known to you. So let's look at the boundary conditions that we get. So there are two.
Sir, one doubt, sir.
Yes.
Sir, in the can you scroll a little above? Sir, for the moment equation for the small element, if we
Yes.
write m plus dm minus m is v plus dv into x plus dx minus vx, the moment equilibrium, sir.
Yes, tell me. Go ahead.
It is coming a little different.
Yes, there is a second order term that will come, right? Can you see there is a second order term where
Sir,
two derivatives are multiplied together?
Yes, sir, but x dv will be ignored now, sir.
Yeah, that's what I'm telling. So the second order, not x dv. I think dx
dx
dv
dv will be ignored because it's very small.
dx dv will be ignored. So two derivative terms will come. That two derivative terms is much smaller than first order terms. So first order derivative terms, then comes the second order derivative terms. As long as we assume very small deflections, right? Very small strains and stresses, we are going to work within the first order derivative terms, not in the second order derivative terms. Okay. Second order derivative terms will lead to second order or square terms, right? It will lead to square terms, which will lead to nonlinear stress deformation relationships and nonlinear deformation, geometric deformations of the beam, which we disregard for your undergraduate courses itself. That's a good question, Abhishek. That's a good point that you have put up. Yeah, there will be a second order term, and you have to avoid the second order term. So neglect the second order term. Okay, neglect those terms, and then you are very safe. I'll come to that. What happens when you do not neglect second order terms? We'll come to that probably. Not now. Probably maybe when we deal with deflections. Okay, and you will definitely see that that's a complicated expressions to solve. Okay, so there are two kinds of boundary conditions. One is a force boundary conditions. The other is a geometry boundary conditions. I think I have spoken about this. Now, force boundary conditions is what you need to solve this moment equation that we just saw, the second order equation. Whereas the geometry boundary conditions will be needed to solve your deflection equation. So we'll talk about that later. But let us see what are the boundary conditions. So the different kinds of beam that you can see are mainly of this, special categories. First is free beam. Free beam is a beam whose boundaries are, there is no support at the boundaries. Okay, it's free. Cantilever beam, where one support is fixed, the other side is free. Simply supported beam, where one is a hinge, the other side is a roller. Then simply support with overhang, where you have one side as hinge and there is a roller in between, not at the side of the beam, in between somewhere. Then you have fixed beams, where both sides are fixed. Then we have prop cantilever beams, where one side is fixed, the other side is a roller. Okay, so these are the general beams that you are going to see. That's what was given here. Now, I hope you understand what do you mean by fixed boundary condition. When I say there is a fixed boundary condition, it means both moment and shear force will be resisted at this section. That means at this point, the beam will neither have any slope nor have any deformation. Okay, so neither beam can rotate, neither beam can deflect at this point. So this point resists both. And therefore, this point you will have both RA and MA to be non-zero. Okay, so that's the boundary condition. Now look at the free boundary conditions. When you say a free boundary conditions, it is free to fall, right? So it can drop down. It can rotate also, like this. Both can happen, right? It can rotate. It's free, right? So you just give a couple here, it will rotate. You just push it downward, it will go downward. So there is no support here. So nobody is resisting the motion at B or at A, right? Therefore, both RA and RB going to be 0 and MA and MB going to be 0. Since they are not resisting any deformation, there won't be any force that is generated. Okay. Therefore, you don't know delta A, delta B are not known, theta and theta B are not known. Cantilever case, free end will also have same thing. So RB and MB should be 0 because it's free. So there is no force that is generated, support force that is generated there. So it's free. Whereas delta B and delta B will be unknown. But delta A and theta A, which are acting at point A, and we know that point A is fixed, therefore they are going to be 0. So these are all geometric boundary conditions, and these are all force boundary conditions. Now look at simply support. What happens in simply support? In a simply support case, the point A, if you look at, the beam is not allowed to move neither upward side nor downward side at point A because it is hinged. But it is allowed to rotate. So if you don't have this support, the beam can rotate like this. Okay, so it is allowed to rotate. Therefore, this support resists only vertical force. And if there is a horizontal force, it will resist the horizontal force, but it will not resist any rotation. Therefore, it will not resist any moment. So moment carrying capacity of that point is 0. Therefore, RA is not 0, but MA is 0. That's the boundary condition there. Similarly, at B point, RB is not 0, but MB is 0 because it will not resist any rotation. Therefore, it doesn't have any moment carrying capacity. Similarly, it will not have any horizontal load carrying capacity. So if you push it horizontally and you don't have this hinge here, the beam will move horizontally, right? Because it's a roller. So it's horizontally also, it cannot take any force. So it's HB is also going to be 0, horizontal force at B. Similarly, you have to look for the boundary conditions. As we have discussed earlier, I hope I have discussed earlier, when your force is not known, then your deformation will be known. When your moment is known, your slope will not be known. So not equal to 0 means not known. Same here. Same here. So RA and RB are known, therefore delta A and delta B are not known. MA and MB are known, therefore theta A and theta B are not known. So it's always complementary. So all of them will be known, the other will have to be find out. Now support with a hang. Here also this support is a hinge, and therefore you know these boundary conditions are going to be, right? These boundary conditions are not unknown, and this point is a ruler, right? Okay, this point is a ruler. Therefore, that boundary conditions is also known. So RC and MC, so at this point, it's a free end, right? This is a free end, so it will not carry any load. So RC and MC going to be equal to 0, whereas delta C and theta C are not known. At A, RA is not equal to 0 because support force will not known to us, but MA is equal to 0. Therefore, delta A is not equal to 0. Sorry, delta A is equal to 0. Similarly, you will get an extra condition delta B to be equal to 0 to solve this problem. Okay. Now look at fixed condition. Similarly, for a fixed conditions, you know, this point is fixed and B point, A and B, both the points are fixed. Therefore, they will not have any deformation. So delta A, delta B, theta A, theta B, all of them is going to be 0. And all your unknowns will be your forces, RA, RB, MA, MB, and all of them are not going to be equal to 0. And this is indeterminate structure. Same here, there is another indeterminate structure whose conditions are also given. Okay. So go through this slide, you know.
Sir?
Yes, we will need this to learn a lot. Yeah, Kanika sir.
Sir, in the case of simply supported beam, sir.
Yes.
At point B we have a I mean, like at point B, just it does not allow vertical movement, but it allows horizontal movement. So
Yes.
Horizontal movement.
Movement.
So
yes.
yeah. So won't there be deformation along the horizontal directions of the rod? Can't it expand?
Yeah, it will be. There will be, yes. If there is a thermal change, yes, it will be. If there is a horizontal load, yes, that will be.
So,
but generally, for a transverse load and of transverse deformation, we don't consider there is a horizontal deformation at B.
okay, so here only transverse load. Okay.
Okay. Most of the cases, unless specified, your horizontal, there won't be any horizontal force or horizontal deformation at B. If there is a inclined load is given or a horizontal load is given, right, or there is a thermal change, then your theta B will have, sorry, at B you will have a horizontal motion, okay, a deformation or a horizontal. Unless specified, you assume that it's a transverse load, and therefore you do not have to consider horizontal deflections. Okay, B is a general, structural solution for many of the structures, right? For frames, where you will have, so this is the condition where you will have both horizontal and both along the axis and transverse to the axis deformations. So these are called frames. So degree of freedom in a beam are this vertical deformation and rotation. Okay, beam member. So let me write it here. Okay, this is a beam member. Degree of freedom. Now if you have a what do you call, if you have a frame member, its degrees of freedom are this. Okay, so you will have let's write it as instead of V, we can write it as U1, U2, V1, V2, theta 1, theta 2. This is frame. Now if you look at axial member, for an axial member, how are you going to have your degrees of freedom? U1, U2, only axial. Torsional member, right, theta 1. So these are the difference in degrees of freedom of various structures. So when we say a normal beam, we do not mean there is any horizontal load or horizontal deformation in the beam. But when I say it's a frame structure, I mean that there is a longitudinal axis deformation available in the member. Okay. Yes, degrees of freedom means that these are free to move. These are the directions it can move. This is not okay. So degrees of freedom means if I have a beam and if it has a point here, so any point in the beam, it has two conditions. One is it can go transverse motion and it can rotate about its previous point. These are the two things that it can have. It cannot go axially or longitudinally away from its previous point. So the longitudinal distance between those points are going to remain fixed. Whereas in a frame structure, the longitudinal distance between these 2 points can be there, right? So one is U1, the other one is U2. In this case, if this is U1, that has to be U1. Okay, so there is no longitudinal difference between 2 points. But in frame structure, there will be difference between these 2 points in longitudinal direction also, apart from V1, V2, and theta 1, theta 2. So point B can have rotation extra with respect to point A. Point B can have a vertical deformation or a transverse deformation different from point A. Point B can have axial deformation different, longitudinal deformation, not axial, or axial is okay, axial deformation different from point A. Whereas in a beam structure, it's not going to happen that way. In a beam structure, point B will have vertical deformation or transverse deformation different from point A. Point B can have rotation different from point B, but not any axial deformation. For an axial member, point B can have axial deformation with respect to point A, but neither transverse nor rotation. These are not allowed. So only degree of freedom allowed is test motion. Okay. For example, if you're catching a train to come to IIT Madras, you are allowed only to come to IIT Madras. You are not allowed to go to Bombay and start, your movie or become a hero, actor. You're not allowed to do that. You're allowed to come to IIT Madras and finish your undergraduate studies. That's the degree of freedom allowed to you. Okay, so here also, if you have a torsion member, only you can have twist. You cannot have neither axial motions nor transverse deformations right? These are not allowed. Yes, Kanika, now you can ask.
So even if the beam's one end is fixed, we can say that it has some DOF, like though it is zero, like point next door will have some.
So when you fix it, so when you put a boundary conditions, those boundary condition has to come up over and above this. Okay. Right. So after you have the degrees of freedom, then only you say the boundary conditions. For example, this case you are talking about, right? So now the boundary conditions tells that you see that I have taken only delta A and theta A, delta B and theta B. Right. I did not take HA, HB because horizontal deformations are not there at all. So these are my allowed degrees of freedom. Now some of these allowed degrees of freedom will be zero because of the constraint or will be known to you. Okay, these are the allowed degrees of freedom. Doesn't mean that these degrees of freedom will be there. The constraint can kill these degrees of freedom, definitely. But these are allowed. For example, right now, the constraint is not allowing to even come to IIT Madras. Right? You have a degree of freedom to coming to IIT Madras, but the constraint is not allowing you to come to IIT Madras. And it has killed that degree of freedom. So the constraint, you know what constraint I'm talking about. So once the constraint is lifted, you have a degree of freedom. Now that degree of freedom is allowed to come only to IIT Madras, not to go somewhere else. Okay. All right. So that's what degrees of freedom are. Okay. Now let's get into some of the assumptions that we made. One of the assumptions we made was, so this figure I think I have explained in the last class itself. So if you have a beam section like this, it can be of any cross section, doesn't matter. There is a neutral axis, which this is not longitudinal axis, this is neutral axis. Okay, and that is within neutral plane. Neutral axis and neutral plane. This is your neutral plane. Okay, the neutral axis lies in the neutral plane, which aligns with your y0 axis. So this is your y-axis, right? And this is your z-axis. So this deformation along y is called in-plane deformation, and the deformation along z is called out-of-plane deformation. Load has to be along y direction, or along y-axis, not direction, along y-axis. Okay, and there is a moment, if the moment acts, that will also act along y line, this axis. Now plane sections remain planes or before and after bending. What does this mean? Let's say there is a structure here, there is a 3D structure you can see here. Okay, a 3D beam, and there are a lot of planes that are cut here. This is one plane, that is another plane, this is another plane. Okay, so the beam you can assume to be made up of many planes. Now when the beam bends, so this is the bend picture of the beam. When the beam bends and there is a compression, you can see there is a compression here, there is a tension here. Whenever that happens, your plane section will get inclined, but it will still remain plane. There won't be any twist or warping in the plane. Okay, the plane section will still remain plane. That's the meaning of this. Right. So when you mean, what do you mean by plane here? They get inclined. You see, they have got inclined, but they remained in the same plane. They have not gone different from another plane like this. Okay. So what happens if you take if you take an axis, and if you take perpendicular one of the line, that line will remain perpendicular to the neutral axis again before and after deformation. So that's one of the very important assumption for small deformation. Yeah, here you see. If you see this picture, so this is a deformed neutral axis, okay? Right? So my MN line was perpendicular to before deformation, will remain perpendicular even after deformation, but it will get inclined a little bit. To remain perpendicular, it has to incline, right? Because this line has inclined. So this is called, and that will follow the plane, right? So the plane will also remain plane. Okay, so this line will get inclined but will remain perpendicular. So the lines normal to the neutral axis remain normal before and after deformation. So that's a very big assumption, and this assumption is due to small strains. Okay, we assume very small strains and no distortion in the beam. If you have a large depth, very deep beam, then this is not valid. Then what happens? It gets a little bit twisted. You see, that becomes your actual deformation. Okay, So that is not what we are assuming. We are assuming that normals remain normal before and after deformation to the neutral axis. Okay.
So in this,
can I finish? Then can you
okay,
ask? Okay, so based on those deformation, there are three theories available for beam. One is Euler-Bernoulli beam theory, and in which we assume that length is much larger than depth, and depth is larger than width. Okay, so L is much larger than D, and D is larger than W. Then you have shear beam theory, which is valid for deep beams. Okay, for deep beams. This is also a nonlinear beam theory. Okay, second order, as you said, second order, there will be relationship between dV. So second order theory is shear beam theory. Then there is Timoshenko, or it is also called Timoshenko beam theory. Okay, where these are deep beams. When I say deep beams, they are depth. They are very deep. They have a large depth, and therefore this assumption of plane section remain plane or normal remain normal before and after deformation is no more valid. They become a little bit twisted. So there is a shear, extra shear that comes into action. Okay. And then what is the next assumption? Length of the longitudinal or length of the neutral axis doesn't change. This is we have seen in the last class itself. Plane section remain plane section perpendicular to the longitudinal axis remain perpendicular before and after deformation. So that is what we said. In plane distortion is negligible. Now that's what I said. So keeping the plane sections to plane, there is a distortion that is neglected. That means it is not allowed. So if there is a distortion, there will be some extension here like this. Warping, that is not allowed. Pure bending is considered. Okay, so this is what we have discussed. Pure bending is a constant bending where shear force is 0, which you can have through 3-point bending, which you can have from the 2 moments given at the beam, not a single moment. If you give a single moment, it will not be. So this is, please pay attention here. This is not a pure bending case. Okay, right. So Kanikeswar, now you can ask your question. Yeah, now let's quantify the strain that is developing in the beam, and let us define what is curvature. Okay, now we have a term called curvature in case of beams, and that's very important to understand. In case of pure bending, when we have a pure bending, let's say this is a cantilever beam I have, and I've given it a pure bending, and it has been like this. Okay, then between 2 points M1 and M2, 2 points which are at a distance of dx before deformation and ds after deformation. So this will form an arc of a circle. Okay, so if you put a normal line here, and if you put a normal line here, they will come and join at a point called O, right? And let's say the radius is given by rho. So radius is M1 and M2 is given by rho. So 1 by rho is called your curvature. Kappa. It's universal symbol, so you can always use kappa for, and it's not K, it's kappa for your curvature. So now you can relate these two. So you can write that dx is equal to rho d theta, right? You can write. I can write that. Okay, and that will lead to this relation. Kappa is equal to d theta by ds. Okay, now which for a small deformation can be assumed to be equal to d theta by dx for small deformation. We'll see what happens when you have large deformation for small deformations, right? So we'll assume that ds is equal to dx for small deformation. Now if I that gives me, this is the we call this the elastic line or the neutral axis or the longitudinal axis, whatever you want to say, of the beam. Now the beam will have width, right? So let's say this is the beam across part of the beam, right? This part of the beam is here, right? So I am looking at M, M1, M2. So this is Mn portion, this is PQ portion, and they are dx distance apart. Okay. We are looking at a line which is EF, which is a y distance above your neutral axis, right? So this was your before deformation. After deformation, it will bend like this. Remember that we are looking for pure bending case, and therefore these two lines will go and join to a point here, right? Some point. Let's say that point is O. So that point is the center of rotation, and therefore that point will subtend an angle to these 2 points, right? And that angle is going to same because it's a straight line. We said that plane section remain plane, and normal to neutral axis will remain normal. So M and N will still stay in a straight line. They were in a straight line. They will remain in a straight line, okay, with the normal neutral axis, right? These 3 points will remain in a straight line. So you see the assumption is useful here. Had that assumption not been there, then M, N, and this point neutral axis wouldn't have been in a same straight line, okay? So the M, E, N, P, F, Q remains in the same straight line before and after deformation. And they subtend the same angle. Okay, let that angle be d theta. All right. I am interested is in the increase in length or the strain that EF has gone in. What is the strain at EF, right? Once I know the strain at EF, I will know strain at every point I can know, right? Because I know Y. I'll replace Y with another value of Y. I'll get the strain at another value. Okay. And you see there is only 2 moments acting here. Therefore, this is a notation for showing pure bending case. Okay. So far, so good. All right. So now look at these 2 points. They're here. Now this point is your dx point, right? This is your dx length. This length has not changed because that is along the neutral axis. Therefore, this has not changed. So please note length dx along neutral axis does not change. Okay, so that remains same. But EF will have a compression, N dash Q dash will have extension, elongation, right? Okay, so we know L0, if the original length is L0, that L0 is dx, right? And that is going to be rho d theta is ds equal to dx. We're assuming this small deformations, okay? So rho d theta is dx. Now this one, let's say it is a distance y apart away from the neutral axis. So the radius that it will form with the center, radius that will form with the center is going to be rho is your rho distance to the neutral axis minus this y, right? So L1 is going to be rho minus y d theta. Okay. Now strain, you know, strain is change in length, deformed length minus original length by L0. So change in length by length. And this is going to be, if you write L1, L1 is going to look like this. So rho minus y d theta, in rho you can put rho d theta, you can put dx. So that becomes dx minus y by rho dx, right? Okay. So your strain is going to be L minus L0 is y by rho dx, and then L0 is again dx, so divided by dx. Okay. So dx cancel each other, it becomes minus y by rho. Why it is minus? Because upper side is going to be compression, right? So that's why the minus automatically has come. Below side, if I go, bottom side of the neutral axis, if you go, this will be tensile because this is a positive sagging moment. So this is going to be tensile, so it will become positive y, right? Now 1 by rho is your curvature kappa, so it can be written as minus kappa y. This is a very important formula. Strain is equal to minus kappa y. This is a very important formula, and you have to remember it all 3 or 4 or 5 years. Okay, where kappa is the curvature, y is the distance of the layer from the neutral axis, rho is the radius of curvature. Okay, so remember that y is distance from neutral axis. That you have to define, that you have to tell. It's the distance from neutral axis, and k is the curvature. And this is your normal strain. That will also I'll write normal strain. Okay, is that understandable? Now, once you know normal strain, you can find normal stress. Okay, so let's before going there, let's have a small deviation. So we said strain x, epsilon x is equal to minus kappa y. Now kappa is constant for a given section. Okay, therefore if I have a given section here and it looks like this, okay, then it's just, then strain, normal strain is going to vary like this, right? Right, so this is along this direction and these are along this direction. This is epsilon x is a function of y, right? So this is your y. So at that y, your strain is this. Okay, and it's varying linearly. Epsilon x varies linearly with respect to y. Y is what? Y is the distance from the neutral axis. So where is y 0? Y is 0 at neutral axis, and therefore epsilon x is 0 at neutral axis. So this is your neutral axis. All right. Okay. And this is a result of our assumption that normal two neutral axes remain normal before and after bending. Okay. Now quickly we will do the shear stress. Once you know shear strain, shear stress is not difficult to find out. So sigma x is going to be E into epsilon x through Hooke's law, right? We are assuming it a linear elastic material, small deformations. So it's going to sigma x is going to be epsilon E into epsilon x, and that it's minus E into y by rho or minus E kappa y. That's your stress. So now the stress is also a linear function of y. So it's like strain. So strain is this. So the stress will also be something like that. So some books will draw it like this, but be careful with the arrows. The arrows are on this direction because that represent tensiles. The arrows on this direction that represent compression on the member. Okay. All right. Just be careful with the arrows. Other than you can draw it this way. You can just take another line here and draw it like this. It's up to you, but be careful with the arrows. Okay, so far so good. So we know now how to find stress, the stress in terms of curvature and stress anywhere within the cross section. One thing I would say here that the stress along the width is assumed to be constant and doesn't change along the width. Okay, it remains same as it is. So if I have a width here like this, the stress is going to be something like that all through. Okay, it doesn't change. That's an assumption. That's not true. So we are not doing any analysis on different planes along the width. We are doing only analysis along the y-axis, the xy plane. Okay, so with the plane at which z is 0, we are doing analysis on that plane, and we're assuming that it's across, plus minus whatever z is there, it's same. Okay, so with that I'll stop. We'll go to next part in the next class. That means the calculation of new neutral axis. So you can see if you bend a wood, you will see a failure like this. The failure clearly tells the stress has been like that, right? You had a straight line here before, which has become something like this. It clearly tells there was a compression on one side and tension on the other side. Okay, so this is what I was telling. It is assumed to be constant along the width. This is an assumption. This is not Exactly true. But as long as you have small strains, small deformations, and you are working in Euler boundary theory, this is all okay. You don't have to worry about it. They will be slightly different at the boundaries, but that you don't have to worry much. All right. This is how it looks like if you have a section. So that's how it is, constant. But its magnitude will go up and down as far as your sectional understanding is. So it's like this linear, the magnitude. And neutral axis or neutral plane, it will have a zero stress. Right, same thing is drawn for an I section. We'll talk about section in some day. What are the different sections that are used for design of beams? That we'll talk once we go to composite sections. Okay, so if there is a moment that is acting like this, so there is a compression on the top and tensile in the bottom. All right, with that I'll stop. We'll do with the location and calculation of neutral axis in the next class, and then we'll do a few problems, one or two.